Okay, so we're going to recall the events of the resting membrane potential very generally. And feel free to stop me if you have any questions. And we're starting off by looking at this neuron. So this is our neuron here on the left. And we said that the inside of the neuron was more negative. The outside of the neuron was more positively charged. And that ended up being a membrane potential of negative 70 millivolts. Okay. And so the events we spoke about at length were really describing how we got that negative 70. Okay, so that's what we're going to review here in a very general way. So we'll start by looking at our cell. So this is representing a neuron. And we'll start by looking at some of the structures or features that are present on this neuron. So for one, we have the sodium-potassium pump. And we saw that the sodium-potassium pump represented or was responsible for directly 20% of that resting membrane potential, and then indirectly 80% of that resting membrane potential. We mentioned that it helped to pump potassium into the cell, so this is potassium, and then sodium out of the cell. So this is our sodium. So 2 potassium in, 3 sodium out. And that's kind of the first feature that we have on this cell. We also have sodium leak channels. Now we have many more, 25 times more to be specific, potassium leak channels than we do sodium leak channels, right? Okay, so this is where we can start kind of generally going over the steps of how we got this. So the first thing is that the permeability for potassium is greater than the permeability for sodium, meaning that there are more potassium channels than sodium channels on the membrane. The second thing we want to start by looking at is the chemical driving force, right? The chemical driving force. And we said that because there's a high concentration of sodium, because of the sodium-potassium pump, outside the cell, pumping the sodium out, and a high concentration of potassium inside the cell, again caused by that sodium-potassium pump, we have the concentration driving force such that sodium wants to move into the cell, according to its concentration gradient, and potassium wants to move out of the cell, also according to its concentration gradient. Okay. The third part of this was looking at the other force. So what was the other force? There's chemical and then electrical. So we look at the EDF, which is the electrical driving force. And now because we have less sodium channels, more potassium channels, we've got more potassium leaving according to its concentration gradient than we have sodium coming in, again, according to that concentration gradient. And so we have a net movement of more positive charge out of the cell than positive charge into the cell. So that leaves behind this negatively charged environment because of that difference in permeability. And consequently, we have a positive environment out here. Okay. And so now we can look more closely at our electrical driving forces according to the separation of charge. So according to that separation of charge, these are 2 positively charged ions. So what direction will they move according to their EDF? Will they move in or out of the cell? Will they move into or out of the cell according to the electrical driving force? So they're both positively charged. Where does positive want to get to? Negative environment or positive environment? The negative environment, right? So they're both going to try to get into the cell according to their EDF, right? So sodium into the cell and potassium is also moving into the cell. Okay, so let's illustrate that on here. Okay, we have sodium. Its CDF is into the cell, so sodium. And we also have its EDF also into the cell. Okay, and then for potassium, we said potassium had a CDF out of the cell. Potassium, but it had an EDF, which is in the opposite direction, moving into the cell. Okay. So with that said, we can then look at combining these two forces and speaking about the ECDF, right? The electrochemical driving force. So that's kind of step 4 here. Combining those forces and looking at the ECDF. So for sodium, what's going to happen for sodium's ECDF? We have two forces moving in the same direction into the cell, so we end up with a strong force moving into the cell. Okay. And we just add those two forces, right? We add the equilibrium potential for sodium, which we said was what? What value? You remember that value? Positive 60. Yeah, I can go ahead and put that here. And then the EDF, which is going to be represented by the membrane potential, we said that was negative 70. And so if we add these two together, we get a very big, large magnitude of this force of about 130 millivolts. Okay, that's the force with which sodium wants to move into the cell. Potassium, on the other hand, we had forces moving in opposite directions. And we spoke about what to do when forces are moving in the opposite direction, right? We're going to look at the membrane potential and the equilibrium potential, and we'll see which of these two values is greater. So the equilibrium potential for potassium was what value? That was negative, but what was the exact value? Negative 94, perfect. So negative 94 was that equilibrium potential. And then for the electrical driving force, we know that's going to be the membrane potential, which is negative 70. And so because they're moving in the opposite direction, we look to see which value is bigger. And because the equilibrium potential is bigger, the chemical driving force is the direction of the ECDF. Okay, so this is going to be out of the cell, but we're going to subtract out the membrane potential, which is representing the electrical driving force. And so we get a weak force out of the cell. Okay, and if we subtract that negative 70 from negative 94, we get negative 24, or a change in 24 millivolts. Okay, and that's the force with which potassium wants to leave the cell. So we got a strong force for sodium going in and a weak force for sodium going out. And when all of this gets to steady state, that is where we observe our negative 70 millivolts. And all that that means is that the inside of the cell is negative 70 with respect to the outside of the cell, and the cell is now at steady state. Okay, and this is what happens in a cell neuron, specifically at rest. Okay. All right. Any questions there? Any questions? Okay, so this is going to be really important to speak about what we're going to move on to talk about today, which is the development of an action potential. And I want to point out that we have the sodium-potassium pump. We have the leak channels, right? Much more potassium leak channels than sodium leak channels. But we have other things going on this neuron. We have voltage-gated channels, we've got calcium channels, we've got ligand-gated channels. So these aren't the only channels that are on this cell, but these are the ones that are contributing to the resting membrane potential specifically. Okay. Okay, so on this graph here, we can see that negative 70 that we've spent some time talking about. But we can also see that from that negative 70, we can do some different things. We can manipulate the membrane potential to generate what's called an action potential. And that is how we can communicate electrical signals along neurons and excitable cells such as muscle cells. Okay? So in this image, we can see membrane potential against time. And we can see this negative 70, which is where that neuron is, chilling out at rest, not receiving or sending any signals. And then we can see what happens as that membrane potential becomes a little bit less negative or more positive. And when it gets to negative 55, something really important happens. A series of events on the cell, which we'll speak about in detail today, occur which allow sodium to rush into the cell, and that makes the membrane potential start to become really positive, really rapidly. And that is the firing of an action potential. Now, after that event, at about positive 30 millivolts, we then begin to slowly reapproach resting, which is phase 2 here. And then we sort of undershoot the membrane potential, and then we get right back to our resting state at negative 70 millivolts. So the resting membrane potential is a really nice reference point to understanding what happens in the action potential.